learn about policy gradient methods, which includes actor critic, and this different way, a new way of doing learning and reinforcement learning. Because we're not going to learn it, well, we are going to learn value functions, but not only value functions. We're going to learn the policy directly, and then hidden state, a glimpse. So this new approach, where we're going to learn the old approach, like you finished last week, whatever, action value methods, where you learn the value of each action, and then usually you pick the max. Instead, we're going to learn the parameters not only of a value function, but primarily of a policy itself. So we don't have to consult the value function to do our policy, and it's going to be a stochastic policy. So we're learning the probabilities, and then we'll update by a gradient ascent, because we're going up the hill to maximize reward. And so why do this? Why do policies rather than value functions? Well, there's actually a whole mess of reasons, none of which are totally compelling, but together I'm pretty compelled. First of all, in many problems, just the policy is a simpler thing. It's policies like, if you're tilted to the right, go push to the left. And something, so it's often very simple. It's often simpler than the value function. The value function could be crinkly and hard to learn. So it just gives you the flexibility that sometimes the policy function is an easier function to learn, simpler function. That's a big reason. Adam.
I just add one thing. So like a good example of something you're working on right now is mountain car. Mountain car, what we call the bang bang policy, which is basically take the action in the direction of your velocity, is not optimal, but it's a very, very good policy. So it's very easy to write down that policy. It's very simple. But then if we look at the value function, it's actually fairly complicated, as you're going to plot in your assignments.
Yeah, so if you're moving in a direction, accelerate. That works pretty well, not optimal. Poker is another one. Well, no, not quite the same. It's another problem where policy-based methods have an advantage, because if you learn poker, you'd have to do things like bluff with a certain percentage, and what that percentage is, it's got to be learned, because it's a function. The right percentage is a function of the problem. And so if you can do. So how are you going to learn to bluff 1/3 of the time with an action value method? You just can't do it. You can't represent that idea unless epsilon happens to be 1/3, or whatever it needs to be to make it allow you to bluff, to do the action 1/3 of the time. And another important thing, theoretically, is we can then smoothly change the policy. Like right now, if you have an action value function, these numbers, and if one number just skips a tiny bit over the other one, you switch. Epsilon greedy now prefers that one. And so this means you get abrupt changes in your policy for a tiny change in the parameters. And that can make the math really awkward. Or to say it more positively, the math is nicer in policy space. You can maybe avoid the max. What if you have 1,000 actions? Instead of doing this computation of the action value of each of the 1,000 actions and then picking the max, which is a lot of work if you're going to do it every millisecond, instead you could just have a policy that says do this, do that, or do this except with some probabilities. So you don't necessarily have to do a max on every step when you have an explicit representation of the policy. And then it actually is much easier to think about biological links this way. Okay, so we've already seen an instance of this. So in chapter 2, we did gradient bandits. Okay, so just remember that. Gradient bandits, we had action preferences. They were random variable H. And we'd use them instead of our action value estimates, Q, to pick actions. Okay? And we did this. We said the probability that the action at time t would be A would be exponential in the preference for action A. So e to the h of A. And then this division thing is just, that just normalizes it so that the probability is sum to 1. So really the idea is it's proportional to exponential. And it's convenient that it's exponential because h, your preference, could become negative. You're going to want to we want to be able to update it. You don't have to run into a wall at 0. So you just allow it to float freely as a real number, and then when you take e to that number, it's always going to be positive. And E is also nice because you take one increment up or down. It's like a geometric change. It's like you increase your chance of that action 10% or decrease by 10%. Okay, so that's our form, and we're going to use this form now, something very similar to this. And then, as before, we had to learn an average reward. And then, remember, this just kind of remember intuitively this rule we had. We had the change in the preference was step size was the reward higher or lower than what it is on average, times, why is that gray? Is that going to, like another build here? No, I don't know why it's gray. It's just gray. So this second term is trying to capture the idea of what action did I do? And so this is going to be, if we've done action A, then this will be 1, and we'll get 1 minus the probability, which will be positive, and we will move the preference up for the action A. If we didn't do action A, assuming we got greater than average reward, if we didn't do action A, this is going to be, or if A is not the action we did, then this is going to be 0, and this whole term will be negative, and we'll move it down. Okay, so anyway, that was from before. Now let's just generalize this to continuous, or to an associative problem where you have state. That's Bandit's non-associative. Now we're going to do it associative. So with associative, we're going to have a preference function. And now, since we're using function approximation, all of our randomness is going to be wrapped up in the parameter, theta. So we're going to have a preference for a state action given a parameter. This function is no longer a random function. It's just all the randomness is here, so this is lowercase. And the simplest form is that it's a linear function. So that's a good one to keep in mind. So we have a feature vector for a state action pair, and we take the inner product of that feature vector with the weight vector. That gives us a number for that, our preference for that action in that state. And that's a good step towards picking actions.
And this is not to be confused with the parameter vector for the value function.
This is not to be confused with the parameter vector for the value function. Yeah. So this, hopefully for you guys, is the first time you've seen theta as a parameter vector. I've tried to excise it from the book. We used to call it theta, and then we called this theta. Now we separate it. One is the weights, and then the parameters for the policy is theta. And in the actor-critic, you have both the actor, which is the policy, and the critic, which is a value function. The value function will have its own set of weights, and those will be W as usual. Okay, but this new thing is going to be called theta. And theta, even though it's a Greek letter, it's just a real vector. R to the, I can't say R to the D anymore because D is used for the dimensionality of the critic of the the value function's feature vector, weight vector, and feature vectors. So I think I call it D prime. It's R to the, could be a different dimensionality than the one used for the value function. Okay. Yeah, and so this, usually we're going to use, we'll use feature vectors for state action pairs for the policy, and we'll use feature vectors of states for the value function, the state value function, as you'll see. Okay, anyway, we have these preferences, and then we take, this is just another way of writing E, just for E to the power of this quantity. So this just means, again, that the action probabilities are exponential in the preferences, and then they're divided by the thing that normalizes them so that they sum up to 1. So that's just one way of parameterizing the policy. You could parameterize any way you want to. And there's a great flexibility. This is an example. And like we're going to have continuous actions before the end of today. And still, so we'll replace this with like a Gaussian distribution, and that'll be just another way of parameterizing the policy. But however we parameterize it, we're going to need this quantity. I thought we're going to need this quantity. Okay, now I don't really like that way of writing it, but it's very compact. Anyway, you're going to need this quantity. It's called the eligibility function, and it's analogous. Like in the simple cases, it's just the feature vector. That's what we're used to. Having the eligibility was the same as the feature vector in the linear case. But in general, for policies, instead, you need the gradient of the natural log of the policy. And once you've chosen this, the parameterization, this follows by calculus. Okay? So this is the choice for this choice. Or for this choice, this is the corresponding eligibility function. For continuous valued actions formed by Gaussian distributions, we'd have to compute it again with calculus, and we get a different answer. Okay? And I'm going to come back and tell you why I don't like this a little bit later. Okay, so here's an example. I call this a short corridor with switched actions, because it's a short corridor. We have a start, we have a goal. We're getting, I think we're getting -1s per step, and you get to the goal, it ends. And we have actions right and left, except here, right takes you this way and left takes you that way. Okay, so it's a simple, it's not a totally simple problem. Now I'm going to make it a little bit harder. All the states look the same. You can't distinguish between the states. Okay? Can't distinguish between the states. So that, when I say that, I'm picking the policy parameterization. The policy parameterization is such that you can't distinguish between the states. In fact, because you can't distinguish between any of the states, the only policy is the probability of going right. 1 minus the probability of going left. That's your whole policy. And that's your whole parameter is the probability, except it's actually not the probability, it's the action preference, which through that equation that I showed you determines the probability. Through the exponential forms the equation, forms the thing. Anyway, we don't even have to worry about that yet. Just look at it, at the problem. What's a good policy? What should you do? All you can do is pick the probability of going right. Should you pick the probability of going right 100%? Just, that would be good. That would be bad. Yeah, if you pick 100% going right, you will never get to the goal. So why did you pick 100% going left? 100% going left, obviously you're never going to get anywhere. Okay, so, and you get -1s all the time. So what we've plotted here is the probability of going right, and then what your performance measure is. Now, performance measure, we probably should talk about that just a little bit. What should you care about? Okay? So remember, we're in the function approximation land. So there are two coherent settings. One is the value of the start state, and the other is average reward. Can't do that discounting stuff. Okay? So it's an episodic problem, so it's natural not to avoid the complexities of average reward and just talk about the value of the start state. Okay? The start state here is S. Okay? And so the value of the start state under some policy, that's our objective. We want to choose theta so as to maximize the value of the start state, which means, the expected return starting from the start state. Now we call that capital J because engineers like to call their objectives capital J. And I'm not easy with it, but I'm going with it. So that's what we're plotting here. And if you do 100% right or 100% left, you'll get -infinity for your performance measure. And, of course, it's always going to be minus because it's -1 per step. And you might hope to get there in just, well, how? So what we're plotting here is it's analytically computed. What is the value of each policy? Like, this is the epsilon greedy policy that goes left. what epsilon is, what do you think epsilon is? Epsilon is always a tenth, I think. Yeah, and so with epsilon a tenth, so that means that with what probability? Oh, I guess it's here. Epsilon one, if epsilon is a tenth, and you're probably going, and assume that you favor going right, but no, you want to go left, but epsilon greedy means you can't go fully left. You'll go 95% left because you're 10% epsilon, and there's only 2 actions. So 10% of the time you'll explore, or you'll pick randomly, and half of those will be towards the other action. So you might be able to do 5% right, and you might be able to do 95% right. And that are these 2 points. That's the performance numbers if you work it out analytically. You actually do better by random action, because if you favor going right, you'll have, well, if you just behave with some randomness, you will eventually stumble on the goal. And it'll just take you longer if you, depending upon the probability. Does that make sense? And we worked out the optimal probability is like 0.6, near 0.6. And that's much better than either epsilon greedy policy. And so how would you find that? You can't find that with an action value method. You can find that with a policy-based method. And here we have some results on this problem with an algorithm called reinforce that I'll explain in a minute, but I just want to show you that, yeah, we can solve this kind of problem. So we're looking at the performance. This is a learning curve, so we have performance. It's the same measure. The reward from your G0 will have or rather the value of S will be the expected value of the return, the first return. Okay, so it's exactly the same measure. And if we get the step size appropriate, like in the red curve, we get very close to the optimal behavior. And we're getting up, so the dashed line is showing the optimal performance. And so with a good step size, we can get very, very close and fairly quickly. If we had a slower step size, we'd come up slowly, we get even more closer to the correct answer. We are doing gradient descent, and we will be approaching the correct answer, the optimal policy. Questions? Okay, so I didn't tell you the algorithm, and I want to get to that. So let me just make sure I've set all the setup. Step 1 is to pick a parameterization. So you pick this function, pi, and then you have your objective, and it could, in this episodic case, you could use the value of the start state, or you'd use an average reward objective. They can both be treated very, very similarly. And then you're going to try to climb the hill in the objective. You know, the gradient gives you a performance as a function of your parameters, theta, and then you're going to, if you try to find the slope and go up that hill to improve your performance, change theta to improve your performance. So the trick is to get this an approximation of the gradient. And there we have this magical result called the policy gradient theorem, which says that the objective is proportional to this thing. And this thing is nice because it has, it doesn't have anything like, you see, it's tricky because when you change the policy, you also change the states you visit. Now, mu is the states, how often you visit each state. But there's nothing here that says like the gradient of mu with respect to theta. That does not appear in this analytically true equation here. I mean, it's a proportionality, but it's otherwise it's, you know, it's just a mathematical statement. These things are equal, So there's that, and then there's the value function, and then there's the gradient of the policy. So this we will know because we know our policy parameterization. We can calculate the gradient. And this we know how to sample or estimate in various ways. And mu, we're gonna run into states as if under mu, because mu is how often we run into states under the target, under the current policy, under the policy given theta. So this pi is pi theta, just to be clear. I'm not showing that explicitly, but pi is pi theta, and this mu is mu pi. And often, actually, I will omit the theta on the gradient. In other words, it's always the gradient with respect to theta in this policy gradient methods. Okay, so this is like a important result, and I'll prove it for you in a little bit. But first, well, I don't know, what are we going to do next? Are we going to prove it? Yeah, we're going to prove it. Okay. So, well, I like to use, well, take over for a minute, Adam.
Great thing about it is that every one of these steps is actually really nicely explained by the thing in bracket there. So the very first step that we start off with is that we're just re-expressing the value function in terms of quantity. You already know that we did an exercise 315, which is that we can write the value function as the sum of the policy probabilities times the action value function. And then go
What
from
happens
there.
next? Yeah. So we have to do calculus. Do you remember calculus?
No. No one remembers that.
Nobody remembers calculus, but we know there's these tables you go and you look up for all the formulas. And so
The matrix cookbook.
the matrix cookbook. So how are we going to do this thing? Gradient. The problem is, remember, pi depends on theta. And so pi depends on theta, and q pi depends on theta because it's through pi. So both those things depend on theta, and we're trying to take the gradient with respect to theta, and so we have to use the product rule because we have a product of two things. And I mean, the sum is no problem, right? The sum, we can just climb inside the sum and take each term, but each term is a product. So the product rule is you take the gradient of one times the other one, and then the gradient of the other times the first one. That's all there is to it. And so we just do that, as you see. And then, that's all the same, that's all the same. Q pi, the gradient of Q pi. Well, we know one of our earlier exercises that we can think about what Q pi is. We can look at its head and say, oh, what's the probability that we'll get to each next state and each reward, and then Q pi will be the reward and the value of the next state. That's what Q pi is. It's the first step you follow the action. What is A? Well, A is given. No, A is given here. Yeah, so A is given, and so we just look ahead and see what's the reward we get, and then the value if we continued from pi prime, from S prime following pi. So that's just true. And then like this, the reward, we can throw that away because theta doesn't change the reward. It doesn't change any of these probabilities because these are not the policy probabilities. So the first part just goes away. And we leave just the second part. And now we realize, oh, we can move the gradient all the way in, because none of this depends on theta, all the way into there, and we get this formula. Okay, and okay, now it's good. It's really good because we've made this complicated thing, but we've gotten back to v pi of a state, and that's where we started. So we can really take this whole thing in, except for S prime, and stick it in here. Okay, so all this stays the same, and then this is supposed to be this thing again, okay, but for S prime. So here we've written this whole thing again, but for S prime, all the way out to S double prime. That's all seem fine? Yeah, I hope there's no mistakes in the write-up here. So we just sort of unrolled it. And so then you can repeat this, and you just keep unrolling and unrolling and unrolling, and it gets really long. But we can probably look at it and understand it. What's really happening? What's the first term? They're all a bunch of terms of the gradient of pi times the action value. So the first term was here. We have the gradient, and then the next one will be, go ahead, pi probabilities, and then a pi q. And the next one will be the same, except it'll have one more term of pi and one more term of the probabilities. So it's really, it's getting, and there's sums. Okay, so you can rewrite this. So you have to think about it for a while. But first you think about all possible states, and then all possible numbers of steps that it might take you to get to that state. So this then, the probability that you'll go from the state of interest to x in 0 steps is going to be like, well, if s is x, then you're happy. Otherwise, that's the only way. Okay, so that would be for k equals 0. Well, let me just, I can probably carry that. But so each one of these terms is going to be a numbers of steps that you can go from s to x. 0 steps? How's the 0 step coming in? I guess the 0.
Very first one.
Yeah, because you still have to sum over all the actions that you might do, and the probability of getting there. Yeah, okay, we're summing over, it's going to sum to 1, and we want you to sum over all the actions, and you'll get just this thing. No, we still sum over the actions here. Yeah, okay, so that's the very first term, is this whole thing. And then the next one will be if you take a 1 step, so then you have to say summing over the actions, and then inside we sum over, so the probability will involve all the other ones. So this thing is I think it's defined intuitively, but it's really exactly those formulas. And this is also what is probably transitioning from each state in k steps. So this thing, actually, we have a good form for that. This is okay, but I guess I'm gonna simplify that later. I'm just saying, okay, so we want to compute, policy gradient theorem is the gradient of objective, which is defined like this, is going to be what it is. Okay, so we've shown that we've reached this form, and we can stick that in here, and now this whole thing in parentheses collapses into be eta. Eta is just the name of that thing, and it's how many time steps you will be in each state S in an average episode. Okay, and that's what and the sum of the etas is the sum of the etas So you have to remember what mu of s is. Mu of s is for an episodic problem. It's the sum of the etas. It's the sum of the etas. So why is I have a parenthesis here? So mu is the sum of the etas. So yeah. So it's a little awkward that we have these two cases. There's the episodic case and the continuing case. In the continuing case, it's sort of natural to think mu is what percentage of time steps we are in each state. But in the episodic case, mu of s is the number of times you visit each state in the expected number of times in a single episode. So take a random episode, how many times you visit each state. You might visit a state twice or 3 times. And that's what mu of s is. And why is there a parenthesis here? I'm not sure why there's a parenthesis there. Oh, there's a step. I've added this, and I've divided by it there. Why have I done that? Why do I have all that extra stuff? It looks like I may have edited this too many times, but this is basically, it seems like I should just be able to just stop here.
On equation 9.3,
Yeah?
on the right-hand side, you say that eta of s divided by sum of etas of s's is equal to mu of s.
So So if I pull out, okay, so and then, but okay, you're right. Okay, good. That gives me the relationship from mu to eta. And this just goes away because I only am requiring proportionality. So the constant of proportionality is the sum of the etas. And then so if you take the rest of that and you rewrite this as mu, okay, then it all works. What?
How does it go away?
How does this go away?
Yeah.
This goes away because we're absorbing, it's a constant.
But doesn't it depend on the policy?
Doesn't it depend on the policy? Would that be a problem? It's not a problem. It can depend on the policy. It would depend on the policy, but it's not a problem. At any moment, it's got to be proportional. Whatever your theta is. So again, the proportionality constant can depend on theta. Okay, good. Good enough anyway. Okay, where did I put my clicker?
Right here on your sweater.
Thank you. God, where would I be without you guys? So that's the theorem. We can fit it on a page if we slide things up. And now we can go forward because we have our great theorem and we can just derive algorithms. So let's reinforce from this idea. Now this derivation is similar to what we did in chapter 2 for the bandits. This is the general case. So we start with our policy grading theorem, and now we have basically we want to turn it into a learning rule. So we're into something, an update we can do on each time step, and this is for general S. And remember, we have now this mu of S is not, I guess. I'm hedging a little bit because I've rewritten the book so many times. I tried it one way and then I tried it the other way. But this is either the proportion of the time you spend in S or the number of times in a typical episode you spend in S. Either way, since you only need a proportionality, it's going to be at least proportional to how often you're in each state under the policy pi. So you can just run pi and you'll run into states, and if you do the update for each state you run into, you don't need to weight by this because it's the fact that you're doing it to the states you run into automatically weights it by this. Okay? So you can get rid of this whole term and by changing the S's, which are dummy variables considering all possible states, to the states that you actually run into. Okay, so I throw away that and I change my S's to S of T's. And we maintain, because I have an expectation, an exact proportionality, or in fact equality, between these two lines. That's the first step, and that's, that was just so wonderful. We got rid of the sum, and we started to bring in the actual things that are occurring at moment by moment. We would like to do that again. We would like to do that to A, okay? But the reason we were able to do it up here is because we had something that we were asking it to be weighted by how often we run into states. In order to do it to A, we'd have to be weighted by how often we do each action. So what would that be? I need a product of the probability of doing A in S. Okay, and I don't have that here. Okay, but if you want something, you should just get it. Okay, you should do it. You should put it in there. And so that's what we're going to do. We're going to put it in there, and we're going to divide by it. Okay. So now we have this. We've got something the probability of doing A, sum over A. So both the sum and the A goes away, and we can just replace it with well, we lose the probability because we lose the sum and the probability, and we adjust the rest with little a replaced by the actual action we took in that state. Okay, so that's kind of nice. Okay, so now this thing comes up a lot. This thing, it's the gradient of the policy divided by the policy for what we did. Okay, and this thing is the eligibility term. This thing is often written as the log gradient of the policy. It's actually exactly this. They're equivalent because the gradient of logs is just divided by the input. So anyway, just keep this is what the eligibility terms looks like, and I will usually write it this way. And we can know this. This is just the gradient of the policy, and that's just the policy is valued at the current state. So we know all those things. The only thing we're not sure of is the value of the state action pair. But we know how to estimate that. So in particular, if we're in reinforced, we just estimate it by the actual return. And this is still an equality because the expectation of this is the expectation of that. And so that's a strict equality. And so that gives us something that we can make is an algorithm. And the algorithm is just to change our parameter vector by that quantity, the sample. See, now we're only going to, we only have a sample of it. We don't have the expectation, but that's what you really need to do stochastic gradient descent. You need a sample of the gradient. In other words, you need some random quantity whose expectation is the gradient, is proportional to the gradient. We don't care about proportionality because we got our factor of alpha in there that we can adjust anyway. So this is reinforce, and the reinforce it is going to move in the direction of the gradient on average. The average or expected update will be in the direction of the gradient, and this is a really strong theoretical property which gives us convergence results. Gradient ascent. Of course, it's sort of a Monte Carlo method. We're using the whole return because that's going to be a bit noisy. But as you saw on the previous on the results on the short corridor problem, we can find the optimal policy. Okay, so that's reinforce, the simplest application of the policy gradient theorem. And now I want to show you the first improvement. Okay, the first improvement is to add a baseline. We did this also in chapter 2. We're just going to stick some arbitrary function of state, and we can stick it right in the policy gradient theorem. And we maintain equality. Any function we want, as long as it's only a function of state, it can't be a function of action. But if it's only a function of state, we can put anything in there, and we still have equality or proportionality to the true gradient. Okay? Now, in order for that to be true, basically, this can't change it, right? So it has to be that that something is 0. And so we're going to show that we sum over action of this term times that, we're going to get 0. And that's why it works. Okay, sum over actions, the baseline times the gradient term. Okay, so obviously, since this doesn't depend on the action, we can move it outside the sum. And we can also move the gradient outside the sum. And so then we look at the baseline times the gradient of the sum. Well, the sum of the probability of doing each action over all the actions, it's got to sum to 1. So we can say the gradient of 1, which is 0, so the whole thing is 0. So we can definitely put a baseline in there, and we won't affect the policy gradient theorem, but it can still make a big difference, because the policy gradient theorem assures us about the expectation, but it doesn't assure us about the variance. And it turns out you can make a big difference if you have a good baseline. This term remains in expectation, baseline 0, remains expectation in the direction of the gradient, but it can be much lower variance if you pick B appropriately. Okay, so what should B be is actually a non-trivial question. In order to minimize the variance, what should it be? And there's something that everyone does, and then it's not clear that it's the right thing. But what everyone does is they use an estimate of the value of that state. Okay, and think about that. Let's say, does this return, compare it to the value of the state value? This is like Q value minus the state value. It's sort of like it's the advantage, or how much better the action is than average. And so it's really, is it going well? Is it going poorly? That's the intuition. Okay, so that's baseline. And if we just take the same problem and we run it with the baseline, we can do much better. So this is the red curve from before, reinforced with no baseline, or the baseline was 0, and we came up closely. But if we have a baseline of well, what baseline am I using in these results? And remember this problem with the corridor, there's no difference between the states, and so you're just learning, we're just learning the average reward. And which is, the average reward is a measure of the estimate of the value of all states have the same value. So we do much better in terms of how quickly, statistically, we can find the value. And this is the algorithm. I think it's useful to draw out the algorithm for everybody, just to make sure it's clear, because we have these two parts. We've got the actor and the critic. We have a sort of a critic now. This is not an actor-critic setup, because we really just have a baseline. We don't have a full critic. We would not call this a critic. Call this a baseline. So it's a value function used as a baseline. So we're going to have two parameters, the policy parameterization in theta and the value function approximation in W. And we'll have two step sizes, alpha and beta, because we have these two learning processes that might proceed at different speeds. We have to initialize the two parameters. Theta could be a different dimensionality, d prime, than our value function. And then, we're going to do this because it's a reinforce, which is basically a Monte Carlo-like algorithm. It's done episode by episode. We're going to say, oh, what's the return? And we're going to update with the return. So we have to assume, the simplest way to talk about that is assume we wait for the whole episode to be done, and then we go back and do the updates during the episode. So we assume we have this episode following pi, and then we go back for over its steps, and we compute the return from each step, and then we compute this sort of error, the difference between the return and the baseline, which is a learned quantity. And then we learn the baseline. So look at this. It's the step size. Ignore the gamma to the t for a moment, because we haven't talked about that. And then we have our error, and then we have the gradient of the value function with respect to the weights. Okay, so this is really the kind of rule we've talked about in the past. If you do have discounting, then you should put in a gamma to the t here. In this chapter, we assume that we're not discounting just because it makes everything a little bit more complicated to think about. And so we just keep doing that here and just assume it's 1. But if you did have it, you'd have a gamma to the t there. Okay, and then anyway, you do update the value function weights, and then you update the policy weights. And you use this remember, what should go here is this thing, right? And it's just that we often will write it this way. It's just mathematically equal. And this way it fits on one line, and so it looks compact, but it also looks fancy with natural logarithms. Okay, it's exactly equivalent. The way you'd actually implement is you do this. Nico.
You said we don't want to use the average reward setting because it makes things more complicated.
Oh, I do like to use it.
But it seems like the differential return would kind of have a built-in sign. So for some reason.
You would. I see what you're thinking, but it's not true, because there'll still be some states where you'll be getting more reward than others. The base differential reward has the reward has a natural sort of baseline, but there'll still be states where you're going to get more reward or less reward, and you want to then have a baseline for those states that takes that into account. So you'd still need a baseline. And I don't want to get you the impression that I don't want to use the average reward case. It's just that, unfortunately, as you've seen, once you start to get into function approximation, you have to distinguish between the two, and so because they're just a little bit different, and to talk clearly, you have to. So now it's full of algorithms like this. We say this is reinforced with baseline episodic case, and there'll be another thing for reinforced with baseline continuing case. Just those are slightly different. Okay, now I've been jabbering at these equations for a while. But we have this nice small class and classroom, so you guys should talk more.
Is the reinforced algorithm would be valid if we do batch version of the reinforced? We store episodes and then we just update parameters for a batch?
Yeah, so let's talk a little about batch versus incremental. There's really a bias in the book towards the incremental or online methods. And you won't see any batch methods in the whole book, I don't think. I like to think that I'm not biased against batch methods, that I just, that they're both useful, and sometimes it's easier to see things in a batch form and easier to think about, and then you have to work harder to convert it to an incremental form. And sometimes it's the other way around. I like to think that everything will eventually be online instead of batch. But in many cases, the algorithms will, you can do with them either way. Could you do reinforce the baseline in the batch mode? Which I guess that would just mean keeping your policy constant while you collect a batch, a large collection of episodes, and then do all these steps over the whole batch. And then you could do it you could roll over the batch multiple times and average the updates. And instead of actually making the updates, you'd compute their average update, and then once you had the whole average for the batch, you would then make an update. And you might get better results. Less noisy results. Any other comments? Good.
You're calculating the estimated value of the function. Still, you're updating W, so you're still calculating the values of states.
Yes.
So what's the benefit of doing policy gradient if you're going to calculate the values of the states? Why can't we just use that in some way to give a probability-based movement?
Well, you would need state action values. You need action values to turn it into a policy, right? So let's interpret your action. Say, well, here we're learning values, so why don't we just learn state values and be done with it? Yeah, you just have to go back to all the things I listed for you. Or you can go to the short corridor problem. If you did that in the short corridor problem, you wouldn't be able to learn that you need to go right with probability 0.6. If you had action values, you'd be stuck doing one of the two bad epsilon greedy choices.
What if you just do a probability based?
So you might do like exponential function in the action values. Okay, but then you're going to have the problem is, think about it. You learn the action values better and better, and as you learn what they're supposed to be, that will determine the difference between the values of the two actions will determine the probabilities with which you do the two actions. Okay, so now you could have like a temperature parameter also to your softmax. And but you either get stuck doing the percentages that would follow by the difference between the values, which you don't really want. Because then you're not able to pick the percentage that's appropriate for the problem. Or you have to pick the temperature parameters so as to get the right distribution, the right probabilities for the actions. It just doesn't work. It doesn't give you a way to learn the correct probabilities. They would follow from the values. So if one action is better than the other, let's say this is one unit better than the other action, what then should the probabilities be? And should they be different if the units were 2? No. It's a totally separate issue what the probabilities should be for each action. It has to be learned separately. So there's that, and you want to learn probabilities. The function may be smoother in the policy space. And all the other ones are still really, really relevant. Okay. Here we've learned a state value function, and we've used it as a baseline. Okay, but we haven't used it for bootstrapping. We're still using the actual return as our target. We're using it. this is our error. The error is between, this is a baseline, but our target, or our, we're still using the full return. So we're not getting any bootstrapping effect. Okay, and so if you do try to do bootstrapping, then you get to the actor-critic setup. Okay, so the actor-critic setup, we have both a policy and a state value function. We form the TD error, which is a bootstrapping thing, and that TD error is used to update both the value function and the policy, which we now call the actor and the critic. So if we start with reinforce with the baseline, and now we just replace the return with like an n-step return, or really you want to replace it with a one-step return, at least to start with. A one-step return is the first reward plus gamma times if you have gamma. If you have gamma, it's the first reward plus gamma times the value of the next state. If you're in the differential reward setting, it'll be r minus the average reward plus the value of the next state. But either way, after you subtract out the value of the first state, the thing in parentheses is now our familiar TD error. It's what we call TD delta. Okay, so it just becomes alpha delta times the eligibility term. And maybe now it's clear why we want to call it an eligibility term. It's going to be like the eligibility E, and then when we make a lambda version of it, it'll become the trace of this quantity. It'll become, instead of bumping up each time the feature vector occurs, we're going to bump up each proportional to this quantity, okay, to that gradient. Okay, and so as an algorithm, so this is the full algorithm with eligibility traces. So we have our two parameterization, we have our two step size. We actually have a third step size, eta, actually, because I'm going to do now, just for variety, I'm going to do the differential reward case with average reward. Okay, so like if you look at our delta is going to have an r minus r bar term. Okay, so and that's the third step size. The third step size, eta, is going to be used to learn r bar. Okay, so alpha, beta, the actor, the critic, and the average reward. So I'm going to have two sets of weights, of course, one for the actor, one for the critic, and they'll each have their own eligibility trace, a z theta and a z w, and I think they have their own lambda. I don't see lambdas listed up here, but if you look at the actual algorithm, we're going to have we'll have a different lambda value for the w and a different lambda value for theta, potentially a different value. And so, and then since we are differential reward, we're not episodic, we don't have to worry about episodes. We're just all these steps are just going to happen every time step. And there is going to be no termination. And so this line's not needed, and I deleted that from the draft of the book just today. So we're just going to do these steps every time. Okay, and so what happens every time? Well, we pick an action, we do it, we see what happens. We can form our TD error. Did we get more or less reward than average? And did we go from a place where we expected less to a place we expected more? We look at the change in the estimated value, and that's going to be then used for all of the updates. They're all going to use delta. In particular, the average reward estimate will be updated using delta. And then we update the eligibility traces. They're all fading away with lambda, and the different lambdas for the two cases. And in one case, we have just the usual increment to the eligibility trace, so it's proportional to the gradient of the value function with respect to the weights. In the other case, we have the gradient of the log probabilities with respect to the policy parameter. And then we do our updates. They're just step size, TD error times the appropriate eligibility trace. And that's the whole thing. We just do that every time step. And that's active critic. It's kind of an elegant algorithm. And it's very incremental. And just has things replicated a bunch of times. Any questions about that? Okay. This is policy gradient. Yeah, you're getting it kind of fast today, but it's not so strange. It builds on everything you've already learned. We have a critic in there, which is just the same as your value function you've learned. Now we have a similar sort of update for the policy parameters. It takes into account the nonlinearity of the policy function. Okay, so let's try now to go to continuous valued action. Okay, so we're going to have our action that will go over the real space, over the real, just for, it could be multidimensional, but let's begin with a one-dimensional continuous action. And we're going to pick it from we have to parameterize it. We have to write down a pi of SA, theta. Okay, so, or probability of doing each action, given a state and a theta. And so we're proposing to do it according to Gaussian distribution. So you will pick a mean, and you'll pick a width. And then you will, by picking them, I mean the parameters will specify a mean and a width. And then the actual action will be chosen from a normal distribution with that center and that width. Okay? And so you guys know how normal distributions work. They have a center and they have a width. And here's a one right in the middle that's very peaked and very narrow. And there's a wider one, and yellow one is wider still. And so it's the center is the mean, we're going to go ahead and call it mu, even though it collides a little bit with the other mu. And then we have a variance, which is sigma squared. Okay, so when you write, and then we're going to, so this actually is the equation for the normal distribution with indicated mean and variance. So how are we going to come up with these? We have to parameterize the mean and the variance. And so we're going to think of our overall parameter vector theta as having two parts, one for the mean and one for the variance. Okay, so that this big vector has these two parts. And so the mean then for a state will be the inner product of that portion of the parameter vector that corresponds to the mean times a feature vector for the mean and that state. Okay, and we take that inner product. So it'll be linear in that way. That'll determine the mean. And now the variance is similar. We'll have a different portion of the parameter vector and a potentially different feature vector for the states. Take their inner product, but that could be negative. And variances, or standard deviations, actually, I guess. Standard deviations, you don't want them to be negative. And so we take e to that power. And then even if the inner product goes negative, we still have something that's always positive. And it means, again, that we can take sort of geometric steps in the variance. If we've got something that's pretty wide, then it moves more quickly, wider, than if it's very narrow. If it's very narrow, it's going to be making smaller steps in the variance. It's a good form. Okay, and then so then this then gives us the mean and the variance, and then we apply the standard formula for a Gaussian distribution, which is this one. Okay, so now we've parameterized our policy for a continuous normal distribution. What's the next step we have to do? We have to compute the eligibility function. Every time you pick a new parameterization, you have to use calculus and compute the new eligibility functions. And we're not going to go through that, but I'm going to go ahead and show you the answers. And you can think about, at least the left-hand side, this is what you need. You need the gradient of the policy divided by the policy. And you have two parts to it. You have the part that's due to the mean and part that's due to the standard deviation. And if you do your calculus, you can just calculate what these things are. And this is what they end up being. And let's look at them, and they actually make really good sense. Because remember, this is a thing that's going to be combined with a measure of, is it doing good or is it bad? You'll multiply this thing, the eligibility term, times delta. And so delta says, is it good or it's bad? So let's assume it's good, so that we're going to multiply this times a positive quantity. And so what would happen? Well, at the heart of this is an A minus mu term. Okay? So it's going to look at this action. And so, like, suppose you had the action is just a continuous number, right? And so it's going to, that A minus mu is the action that I took bigger than the mean action or less than the mean action? So did I choose somewhat higher than usual or somewhat lower than usual on this time step? Okay? And if I chose somewhat higher than usual, this is going to be positive. And so now I'm going to update my weight vector so that if it was good, so that my mean is increased. If I chose something high and it was good, it'll increase it. Now it's dividing by the variance. The variance, that's the variance, yes. Dividing by the variance, does that make sense? That's saying that if the variance is big, I'm going to move less. The reason that makes sense is if your variance is large, that means you're very flat, very low hump. And so it does you little good to move. If you move, it just doesn't help you that much. The overall increase is small because, if you move over a bit and it's very smooth, it's very flat, your performance is not improved very much. So that's why it falls out of the gradient. This term, now again we have an action minus the mean, but then we're going to square it. So it's saying, and then we're going to subtract that. We're going to subtract 1 from that. Okay? So you have to think about what this is, right? Now this is the variance we're dividing by, and the variance is the expected value of the square. So if the square of the deviation from the mean, this is the deviation from the mean, and we're squaring it. So like in expectation, this ratio is 1. You with me? Yeah, so since we're subtracting 1 from it, it'll be positive if the action we took was more variable than an average action. And it will be it'll be positive if we did a wide, and actually what that turns out to be is if we've sampled an action that's outside one standard deviation, then this will be positive. Because if we sampled something near the center of our thing, then this will be negative. So basically, this is was this choice outside the one standard deviation or inside one standard deviation? If we say we were outside, this will be positive, and if it was good, then we're going to increase the parameters in such a way that the variance goes up. So if we tried something outside one standard deviation and it was good, we're going to now widen our range of exploration. We're going to increase our standard deviation. Anyway, I just wanted to give you a little intuition that you can come up with these things and they actually do make sense. I mean, I might be able to create this algorithm I thought really hard, but here I didn't have to create this algorithm. It falls out of the calculus and the parameterization. All right, so that's about all I'm going to say. What we've covered today is, step 1, pick your approximation, pick your parameterization, compute your eligibility functions, and then you're going to do approximate gradient ascent. Use the policy gradient theorem to figure out what the form should be. You can approximate the gradient that comes from the theorem either by reinforce or by baseline or by a full bootstrapping actor-critic method. Adam.
Can I say a couple things about this?
Yes.
So I just want to inject my bias.
Don't you want to use the big stick?
Only if someone's me. I just want to inject my bias because I actually really think this algorithm is really, really elegant. It's fun to implement. And I just wanted to give you a couple of equations I have. So if we look at this picture, one of these Gaussians, what is this saying? Well, this thing is, you can imagine that this is a function of state. And so this is how we're going to select actions as a function of state, right? So we'll take this one, right? It's saying, you know, the mean is at 0, so I'm mostly going to be selecting a mean 0 action, right? So I'm going to be selecting 0. But what does the variance mean in this case? Yeah, it's like this really beautiful, elegant way to inject expiration, right? This thing that's really wide is exploring a lot. There's chance of selecting all these different values all over the place. But when it gets really narrow, the system's certain it's basically selecting the same thing what the mean is. Like that's just such a natural way to think about exploration. And it's a learned exploration game, right? Like this is updated as we're getting data. And so, you know, just to kind of go over this, you know, how do we select actions in this method? If you were writing a program to do this, sample from a normal distribution, right? And like every programming language has this built in. You just put in your mean, variance, and you sample from normal, and that's how you get your actions. It's just so beautiful.
So we don't have to pay epsilon.
Yeah.
Expiration is learning.
Anyway, I just really like this, and I wanted to convince you guys all run home and implement it. It's just so elegant. Now we're doing continuous action, right? Like, we don't have this crutch of discrete actions and maximizing over possibly a really big set. And the example that I often give, I think Delp used to use this one. Golf. So we did golf way back in the AVT chapter, right? And we could just think of being on the green. So, you know, remember golf is this really stupid, I think it's a Scottish game. Really, really dumb game, right? You have this tiny ball, you have this club, and you try to hit it in a hole really far away. Only in Scotland would that seem like fun. Anyway, if you're on the green and you're putting, you know, you could try to discretize that action space, but that's really is a natural continuous action, right? You want to have a little bit of power or a lot of power, or maybe the guy that cut the green was lazy and there's like a rough patch in the green, so you might want to use more power. It's just a really, really natural continuous action problem. It would be crude to discretize that space and try to use classical discrete action methods there. Yeah, that's what I want to say with that, just because I'm such a big fan. And now we're going to learn about bonding keys. Right?
Yeah, bonding keys. I guess I want to just, one last slide, just some really general strategy. I think we solved it. Generate these things which at continuous times are generating spikes, and they adjust when the spikes happen, and the physics-like differential equations that are generating the spikes. You could use. I'm just trying to encourage you to think of some weird way of generating actions. You can have Gaussians, you can have any distribution, you can have exponential distributions, you can use mixings of things, you can have things that drift up and down. There's real opportunities for doing imaginative things here once you have policies that are parameterized. Okay, so I'm just going to say a little bit about handling hidden state, and you know what it is and what to do about it. I think you have some idea. Sometimes the environment includes things that you can't see. Okay, so the state, if you can't see it, then and they're important, and they're part of the state, you can't see it, they're hidden from you, and So what way we often talk about it is we say that the world gives us observations instead of state. And or we often talk about the world being non-Markov. It all just means these things. And you might think that it would change everything, but that would be a problem because all real problems will involve hidden state in these senses. Even if you're approximating the hidden state, it's going to be imperfect. And if you're doing function approximation, you really are in this realm. Our methods, because we bootstrap and things like that, we're sort of relying on the world being somewhat state-like and somewhat Markov. So what are we going to do when we become more realistic and realize that the world doesn't give a state? So the first thing to remember is not to panic. It's going to be okay, because actually it's not that different. Okay, the first thing to do is to use the things you know about already. Or actually, I guess I want to say it the other way. People usually panic, and they introduce the whole mathematical theory, POMDPs, hidden Markov models, and then they say, well, we have to have complete models of the underlying hidden things, which is crazy, because if they're hidden and they're underlying, how could you have good models of them? I mean, you don't even know what they are. You don't know what they're going, what hidden states are transitioning, but these guys, they really assume they have a complete transition model in the hidden states. Okay, and then they go on and they say they do extensive work to figure out what are the hidden states, right? HMMs, their base thing is I can only see these observations, so I'm going to figure out what's the underlying states, what state I'm in, and it's like really computationally intensive just to get a guess about the probability distribution over underlying states. And so it's so hard even to know when you're in which state. How the hell are you gonna have how the hell does it make sense to assume that you know the transition probabilities, the true transition probabilities amongst the hidden things? That's the normal assumption.
The way I think about this is that let's think of like POMDPs and doing SLAM, and you have a robot. You might have an awesome engineer that can actually come up with one of these motion models for you, but then everyone's robot changes. Like we had this robot, and the wheels would warp when it would drive, and so that changed the model of the robot. And you could try to bring in your engineer again, but you can't rely on the agent learning that, because it's actually mapping from something it can observe, like observations, to something it can observe, which is the hidden state. So it could never learn that without the help of a human. The human would either have to provide supervised samples or just give it a whole new model. It's an impossible learning problem.
Now, there would be those who say it's not impossible, you just have to use really fancy math and do a whole lot of work. And it's kind of true that it's not, I mean, it is sort of amazing that you can do it at all. But it's not, we don't think it's a good strategy. If you look at the actual results that people have, it doesn't work out very well. I always thought that if you proposed POMDPs or hidden Markov models, and you say, okay, we could do this, and then you look at the results, you should say, okay, that didn't work. We should stop that. But somehow science doesn't work that way. They did this, they did all this work, they made all this math, and it just lives on and on, despite the fact that everything is intractable. They used to be able, they could do, like less than 10 hidden states underlying. And now they could do more. They get up to several hundred. Or maybe they can do thousands, okay? But the world has exponential numbers of states. This is, yeah, it just doesn't work. Yeah. Okay, so we don't want to overact. And anyway, just go along with Adam and I and take the other side. Well, why do we have to do all this crazy stuff? Why can't we just do our normal things? Or maybe there's nothing you can do. Maybe there's nothing you can do. If your approximate state is really poor, then any policy on it is going to be poor. you're really in need here to assess what should you expect. Okay, but use your tools. Function approximation is number one. Features can be anything. Features have to tell you about the state, but it's easy for them to obscure information, and like your natural features would be the sensors of your robot, and the sensors of the robot will not report everything about the world. In particular, they can't see behind walls into the next room and into miles away. But nothing in our theory relies on the features being Markov. Because we're using function approximation, we're already happily living in the non-Markov land, and we are effectively have observations. So everything is fine, really. We can go ahead and use our methods. Now, what we don't get is if you have to make a decision based on something that you can't see, that's not part of your observation, you won't be able to. Of course, your policy is only parameterized as a function of what it can see, or parameterized in the way it's parameterized. And if it's parameterized as a function of sensors, and the sensors can't see things, then your actions can't depend on those things. The only way to do that is to change what your is to remember things about the past. Okay, but we can just go ahead, just use function approximation. Things work pretty well. Things don't change radically just because we don't have a Markov representation. Eligibility traces are also less reliant on state. Just the same way because they're a movement towards Monte Carlo methods, and Monte Carlo methods are less reliant on state. Bootstrapping is one way which we rely on state, or rather, I would say we try to take advantage of state. So we can add, moving towards Monte Carlo methods, reduce the damage that might be caused by hidden state. And you remember about the bound on approximation, the fact that as lambda gets long, we approach Monte Carlo, we do better. It's really better in this worst case sense. If our world is not Markov, then Monte Carlo will do better. If our world is effectively Markov, then we will do better by doing bootstrapping, and we'll want lambda to be lower, or we'd like an n-step methods to have a smaller n. And so it's important at this point to remember why we ever do bootstrapping. It's because you can be much more efficient. You can learn much faster if you can bootstrap. Not in every case, but often. And it's a big effect on large problems. So I've told you how not to panic and how to use your tools and to embrace the approximation and the eligibility traces. But really, the long-term solution is you need a way to change your state representation, you need some way of remembering old things. If you can't see something and you've never been able to have information about it, then you're sort of screwed, but you're sort of not screwed because you can't blame yourself for not remembering something that you never saw. But in general, you have to have a recurrent process for updating your approximate state, and it's going to always be imperfect, and you'll have to work on this. So this is just a big thing that the agent always has to do, and even though it really is a big way even though we haven't talked about it in the book, but it's really important. And so let's kind of look at how that would be. Okay, so let's just go back, step way back. What's our architecture look like? Well, our architecture, I like to think of it having two parts, and the two parts are like above and below this line. Okay, everything below this line is interacting with the world, learning. This all has to be fast. As fast as the world runs, we have to see its state, we have to pick an action, and we have to see the reward. We have to learn these things because we're going to learning online. And if we do something that works out badly, we want to change our policy right away. So there's all this stuff is happening here. It has to be fast. And whereas we were talking about the planning and building a model, at least the planning part, which is potentially slow, you can allow it to be slow. It can just slowly operate in the background. So we have a background and we have a foreground. And so that's our big picture. I drew that other line up top where the actions and the rewards and knowledge of the state can also inform the model learning process. So foreground and background. Now right here in the foreground is where we need to make a change. So in the foreground, we have to add a new box, which I call U for state update. And this box here will produce states. It will receive observations from the world. So we're going to receive some arbitrary data from the world, sensors, observations, and we also can see the actions that we've made. This A is the same A as that one. And then we see the last state. And based on those three inputs, we're producing a new state. And so this box here is the state update process. And that's what we have to add. And we have to think about this. It's going to be something that will be learned, adapted over time. And this state update is our new box. That's it's not not at all in the book, except a tiny bit in the last chapter. And something that there's a bunch of there is a bunch of relevant work. We're interested in predictive state representations and things like that. There's a lot of work on it, and a lot of work that's not very good. But yeah, U is a big research topic for me right now. It's also in the foreground. It's got to run every time step because this is going to produces the state, and the state is what you're going to use to pick your action. Then I have a bunch of comments on it. The agent state. This is actually meant to be sort of a new term. Agent state, agent's representation of state. It's whatever the agent is using as its state. It's not the state of the whole agent, including all the weights. It's whatever summary of the interaction with the world that the agent is using to make its decisions. Okay? So it's using as state in picking its actions, in estimating its values, and in sending to the model to use in planning. The planning will be state to state. So in general, this is different from other concepts such as the Markov state or the internal latent state of the environment. That's not what the agent state is. It's not at all the latent state or the hidden state of the world as in POMDPs. It's not the same as the complete summary of the interaction, which would be the information state. Maybe that'd be what the agent state would ideally be. And we can more explicitly describe the state as a function U that takes 3 arguments and produces the new state. And in fact, things like Bayes' rule are instances of this equation where you're making certain assumptions and you perform the update in a certain way. K-order Markov history-based methods would also be an instance. Everything is an instance of this general idea, but we need to think about it in a general way and make progress with it. It needs to be done in the foreground, the planner. The planner will only see these constructed states. It will never work with latent states, hidden states, imagined internal states. So things like POMDPs and HMMs, they all do their planning in terms of the hidden states and the observations. Whereas my planner here will never see the observations and never imagine observations and never imagine the latent states of the world. It just thinks about the summaries that it's used here, the agent states. So the planning will always be state to state in the agent state. What else do I want to say about this? I guess that's it. We've seen how we can work with policies directly, with or without learning value functions in addition, and a glimpse of how you can do continuous actions, and a glimpse of how you can handle hidden state. That's really what I wanted to do today. And so, anything you want to talk about?
You introduced the policy gradient methods as a way to deal with problems with function approximation, where you have
the theory of function approximation, because you have these discontinuous jumps when you do epsilon greedy methods.
Right, but the example with the corridor was that you can only see one state. The agent state is just one state, and
Yeah.
all these hidden states that you can't see. And now you're saying we should improve the agent state so that we don't
Yeah.
have this problem anymore.
Yeah, right,
So
right.
if we have a good function approximation, do we have to worry about policy gradients still? Or can
You
we-
still do. That short corridor was the simplest example I could think of to show where you needed to learn a specific probability of doing individual actions. But you know, the poker example is real. You really have to learn to bluff with certain probabilities depending on what's in your hand. And in general, there's no solution for that. Even with the best state representation, you have to learn probabilities.
We're always going to have to deal with state areas, and even if we have a process that's trying to build better state representation, we're still going to be things that look the same. So we're not going to get away from that. We'll always be looking for resources.
So, in light of what you said about how policy gradient can be better than value-based methods, why would we use value-based methods?
All I said was that they can be. So the other statement is also true. Value-based methods can be better than policy-based methods. If the value function is simple and the policy is intricate, they go the other way around. It can go either way. So I really, in my own thoughts, I am sort of agnostic. You know, I like the fact that we have both strategies. I guess I have a soft spot in my mind for actor-critic methods because I think it's because I did my thesis on it so long ago. Yeah. So you know what happened was when I was starting, they were very popular, the actor-critic methods, policy-based methods, and then we found Q-learning, and we were all excited about all the value function-based methods, and they became popular. But then they said, oh, there's these theoretical problems and other things they can't do. And so then it swung the other way back towards policy-based methods. And I guess nowadays, the fashion, they're both in fashion. There really isn't really a strong swing either way right at the moment. Yeah, I know. What is fashion? You know, we work at DeepMind, so we want to see what fashion is. We often look around DeepMind. What do those guys do? What do we do? Yeah, they have their favorite method that I don't never why they call it raw beast, and I don't know what it means. But it's a big policy gradient method, and they like the policy gradient methods for many cases. Cody.
You mentioned in the book, one of the reasons you're interested in these methods is because it's a way to reject higher knowledge.
Yeah, I said that, didn't I?
Yeah, I know you touched on it so much in this one. I was curious what that actually means and what kind of.
Yeah, I guess that's real. I guess I'm going to stand behind that. That you may have a feeling about what the policy should be, and like, you know, you don't want this AI system to go and like do something and then try to tell you it was doing the optimal thing. You just said, okay, never step off the cliff or something like that. Okay, so by picking the policy parameterization, you can often inject your knowledge about what things you should consider and not consider. So, I mean, you can do that in the value function as well. You can inject world knowledge, but the world knowledge may be more naturally expressed as a policy prescription. And so you can build that in and specify it that way. Yeah, I really think either one could happen. Either one could be more natural.
So we learned the actor critic, which is basically like two function approximations, one for the policy and one for the values. And now you're saying that if we were to deal with real problems which have really partial observable properties and everything, we would have to learn a third function approximation basically for the mapping from the observations to the function states, right? More or less. Because this should also
The state update.
right?
We need the state update. I say we need the value function, we need a policy, and we need a model. So there's 4 boxes
Right, that's true.
in that picture. There's at least 4 boxes. I think of myself as kind of a minimalist. I don't want to add unnecessary things, but I think we absolutely need those 4 things.
I'm curious about what the actor critic is actually doing. So it seems like even if the value function is not accurate, the policy can still be good policy.
Yeah, so remember the critic is just there to be a baseline, and your expectation is in the correct direction, whatever the critic is, whatever the baseline is. Yeah, whatever, I have to separate the baseline case from the critic case. But whatever the baseline is, it doesn't affect your expected update, but it just affects the variance. So there's a sense there which can only mess you up so much, or it only help you so much. Now the critic, there's introduce the value function into the action value estimate as well, into the target part, and then you're doing real bootstrapping. You're not doing bootstrapping just because you have a baseline. You're just trying to reduce the variance without bootstrapping.
So the policy grading methods we so far talked about is with on-policy learning, right?
So we've talked just about on-policy learning today, and off-policy learning, off-policy versions of policy gradient methods also exist. They're much less studied. But they're a really interesting topic, yeah. So we're working on them. Martha and Eric are working on them right now. Yeah, but it's just the first few questions. It's really an open area. So that's why, of course, the book is just the introductory book. We can't cover all the things anyway, but yeah, it's important to notice that what we've talked about today is all on policy, and as usual, things just get a little bit more complicated and subtle as you go to off policy. But so you guys should be all set up. You learn the dimensions, and this is the way I think is a good way to do research. You say, oh, we understand this and we understand that, but we don't understand the combination of the two yet. So we understand policy gradient, for example. We understand off-policy methods for value functions, but we don't understand off-policy policy gradient yet, or at least not all of it. Good way to do research. Works for me. Okay, so thanks for staying extra time. We just got, we will meet next Friday. The next 2 classes that are specifically for 609 are the Monte Carlo Tree Search class on Thursday at the regular time. And then we will cover off-policy action value methods. And yeah, I've saved the best for last, the hardest for last.
Start reading now.
And yeah, I don't know, did you notice it's the whole starred chapter. Chapter 11, the bankrupt chapter, is starred.
Star means run.
Star means run. And we're only going to do it in one course, so we can't really do it thoroughly. But we'll give you a taste of it and a feeling for it. Okay? Thanks. See you.